Okay,
And
my voice.
yeah,
Okay,
your
fine.
presentation is good. Yeah.
Okay, fine. Okay. So, uh, a very good morning, one and all. Uh, I warmly welcome the faculty member, the students of Parul Institute of Technology, the IW student chapter, office barriers, and the team of the organizing team of this webinar. Uh, I'm very pleased to be here for giving a talk on welding metallurgy of stainless steels. All right. Uh, just please allow me to off my screen so that we have a proper bandwidth. Okay, fine. Okay, sorry for interruption. Okay, great. Now again, the screen is appearing.
Yes, sir.
Okay,
Yeah.
fine. Great. Great. Okay. So now the contents of the presentation I would like to go through is understanding microstructure property relationship, because when we are talking about welding metallurgy, obviously we have to uh, understand the this relationship. Then I will touch upon the welding metallurgy of martensitic, ferritic, austenitic, and the duplex stainless steel, that is a ferritic austenitic stainless steel. But considering the time of an hour, I think I can barely touch with austenitic and ferritic duplex stainless steel. If some time permits, I will definitely be ready to give insights or technical inputs on the ferritic and martensitic stainless steel as well. So, to begin with the talk, uh, the welded joints, we are making joints for obtaining certain mechanical and corrosion properties, right? And we know that the mechanical properties are depending on the microstructure, right? Weld microstructure. Sometimes as weld condition we use, sometimes we use uh, joints in a post weld heat treatment or heat treated condition. But this microstructure of as weld microstructure will depend on the chemical composition of the base metal and filler and the thermal cycle, right? So there is a interdependency, right? Because input of mechanical properties through microstructure is input through chemical composition and thermal cycle. So, and not only the chemical composition but the thermal cycle, the heating and cooling rate, particularly the rate of cooling, will affect the microstructure. Okay, so in this context, factor affecting thermal cycle, it is worth noting, because when we are uh, studying the thermal cycle, what are the factors supporting thermal cycle? These are welding processes, because most of the time we are dealing with arc welding processes, like shielded metal arc welding, gas tungsten arc welding, gas metal arc welding, submerged arc welding, plasma arc welding, right? So the welding processes, then heat input. I'll also introduce heat input, joint design, thickness of materials, because cooling rate, because the thick plate will undergo fast cooling because of the more surface area available, right? And thin plate will undergo slow cooling. So that is why the cooling rate affects joint design effect, right, or dilution. Then physical properties of the base metal and filler metal, and the welding procedures, right? Right, joint preparation, and obviously the cleaning of the base metal and the backing of filler before going for welding, and the pre and post weld heat treatment, right? So these are the factor affecting the thermal cycle. So what is welding metallurgy is all about. Welding metallurgy is all about microstructure property and weldability, right? So weldability is the it is the behavior of material uh, for towards welding process, right, in a simpler term. So weldability. And okay, so now we are now focusing on the um, welding metallurgy is all about this. So I'll try to explain it in very simpler terms so that the students find it interesting, and they will be inspired to do some work in welding processes for their project work and all this. Okay, so now microstructure properties weldability is all about welding metallurgy. So what are the phenomena involved? Because in a welding, or your screen, you see on the right top is a welding plate. It is in under the welding is in progress. You see a fusion zone where your uh, filler metal or your base metal is melted, right? And you see a heat affected zone just adjacent to the fusion zone, and you see a moving heat source, right? This is the direction of the welding. So many phenomena are involved in welding uh, processes like melting and solidification, because your base metal has to contribute to the weld metal. So base metal, edges of these base metal are partially melted to get mixed with the filler metal. Then the whole uh, um, molten steel with this will be solidifying. Then there will be nucleation and growth because these solidification process. Then there will be phase transformation. Then there will be some segregation and diffusion because if you are welding austenitic, ferritic, duplex, martensitics, right? So the different along elements move here and there. They diffuse into the either phase of ferrite or austenite, and there'll be some segregation as well. Then there may be a precipitation of new phases or some intermetallic compounds, and there will be recrystallization and grain growth, right? And sometimes you end up with embrittlement, your weld cracks, and the thermal expansion, contraction, and the residual stresses, distortion. There are n number of phenomena are involved in a metallurgical or welding metallurgical process. So welding metallurgical. Uh, it is very interesting to study the welding metallurgy. So that is why this. Okay, so now on your screen you see a weld joint. So it is essential to first identify the zone of welding. First, you see the most centered is your weld metal zone, or you see it's a weld deposit. Just adjacent to the weld deposit, you see here over you see a fusion line. Yeah, where my cursor is moving, you see a fusion line. That is the line between the base metal and the weld metal, right? Just adjacent to the fusion zone, you see a certain area where the microstructure has been affected. This area is known as heat affected zone, right? And further away, as you move from the weld center line towards the base metal, you see a unaffected base metal, right? So you now can understand that this deposited weld metal will have a uh, different microstructure when you move from the weld center line to base metal. So these different microstructure as a result of composition, cooling rate, and heat input, right? So variety of microstructure is developed. So now we have to understand certain terms which are very necessary for understanding the welding metallurgy. First is dilution. Just to focus on the figure where my cursor is moving, you see the as I have told you, the base metal is contributing to the weld metal. So now this A and C, what you see, these are the contribution from the base metal in the chemistry of the weld metal. So its percent dilution of base metal is the summation of A plus C divided by the whole of the composite mixture, this A plus B plus C, right? So it is a contribution from the base metal into the weld metal. So you have 100% dilution when you are welding without filler metal, that is in a autogeneous mode. And when you are welding with some filler, you have some contribution from the filler metal. It means filler metal will be melted, and filler metal will fill the groove, and you have a mixture of the filler metal, and you have mixture of the base metal. So uh, uh, you have a almost a composite kind of composition, right? So this is all about either you go for autogeneous or you go for filler metal mode. Okay, so now dilution is an important aspect, because if you closely look at the two figures, you see at the uh, second one figure, the middle figure, where the weld edges are meeting each other. Here over there is a root, some root gap is there. So when they are joining, you have a higher dilution from the base metal. When you have some root opening, there will be somewhat lower dilution from the weld metal. So the dilution is also depending on the joint, weld joint, right? And the uh, composition, and cooling rate. Okay, so second, this is a very important to understand, because on your right hand side you see a weld metal schematic. You see this is a weld metal. Adjacent to the weld metal is, you just look at the fusion boundary. Just between the fusion boundary and your true heat affected zone, right? You have a zone. This pink shaded zone, this is known as partially melting zone, PMZ. This is just because why this PMZ is created. Just look at the left hand side of figure. This is a simple phase diagram. It is showing the temperature versus the composition. You see a composition, certain composition, which is cooling through a liquid region. Then between liquid and solid line, in between these two lines, you have a solid plus liquid structure, and that is your PMZ, that is your partially melted zone. This zone is there where in your partially melted grain boundary. And many metallurgical phenomena are associated with this, sometimes knife line attack, sometimes cracking. And just beyond the partially melted zone, you have a true heat affected zone. True heat affected zone means the zone which has been affected by the thermal cycle. All right. So you understand this, how at a microstructure level, the closeness between these this agreement between these phase diagrams and weld zone regions, how they are correlating. Okay, why we have to correlate, right? Phase diagram with the microstructure. Okay, now the heat input, perhaps in your so students, if you are studying a welding processes, you are knowing about the formula of the heat input. It is the amount of heat delivered into the weld metal. So this heat input is a product of the uh, uh, it's a ratio of the power divided by the welding divided by the electrode speed, right? That is traveling speed, that is mm per minute, and your power is a product of your voltage and amperage, right? And here over you have a coefficient, that is efficiency, eta, and the eta will depend on the various welding processes. So the heat input has unit joule per mm, or you can say the kilojoule per mm. Right? This eta, just I was telling about this efficiency factor. This efficiency factor will depend on the different welding processes, right? Because if you are welding with the submerged arc welding process, it's a factor of 1. It means you have full use of the heat of the arc. It means the process efficiency is 90 to 99%. It means the amount of heat delivered to the from the source to destination, from the electrode to workpiece, is 100%. So in a various amount, like in arc welding processes, other arc welding processes, shielded metal, gas metal, tungsten arc welding, and plasma arc welding, you have some efficiency factor. Okay, so it is heat input has influence on the dilution, heat input influence on the microstructure property. That is why it is essential to understand heat input. Okay, now we are moving on to our main discussions on stainless steel. So I hope now that by this time you are now somewhat clear about the factor affecting the microstructure, because in a given time it is difficult to cover the welding metallurgy aspects. So because what I have tried to explain it through my presentation is very a punchline to understand the welding metallurgy, right? Okay, now we are to discuss about the stainless steel. So you should be knowing that the stainless steel is a material which provide corrosion resistance, and this corrosion resistance property is because of the chromium, at least 10.5% minimum chromium in the composition of the steel. So this chromium has tendency to combine with oxygen, and there is a first topmost layer on the stainless steel, that is chromium oxide film is there. This film is very protective, it is very dense, and it takes care of the corrosion resistance. So that is why the stainless steels have chromium in so there is a big role of chromium in a stainless property. Okay, so now there are mainly 5 types of stainless steels. They are depending on the alloying element present, but they range from the fully austenitic to fully ferritic. This perhaps is red font line, red fonts you can understand in a subsequent slides, because from fully austenitic to fully ferritic, this can be explained through the solidification mode. But there are 5 types are mainly uh, austenitic, ferritic, martensitic, and duplex stainless steel, right? All right. Now, uh, moving on to our discussion of the austenitic stainless steel. As I have told you, austenitic stainless steel are the most common and most weldable stainless steel, and most of the constructions of most of the fabrication make use of the austenitic stainless steel, because they are most weldable. Their crystal structure is face-centered cubic structure, and they are non-magnetic in nature. But unless they are cold work, because whenever they are cold work, some martensite develops, and this martensite is a ferromagnetic in nature, right? So when this austenitic steel is manufactured in a steel mill, the composition is just as it just said that some ferrite will remain in the composition. So this ferrite will, when you are hot rolling, this ferrite will disappear. But when it is cooled down, either through autogenous weld, or when the finished steel product will cool down, this ferrite will again appear in the microstructure. So we will discuss this, the role of ferrite, the small amount of ferrite in a austenitic stainless steel. It is a big role to play, right? So now it is introduction about the stainless steel, right? Now, austenitic stainless steel, and this austenitic stainless steel have in composition generally 16 to 26% of chromium, 8 to 12, 24% of nickel plus manganese, and up to 0.03 percentage in low carbon grade stainless steel. And there are also other alloying elements like molybdenum, titanium, niobium, or columbium, or tantalum. So there is a role of every alloying element. This nickel and manganese makes it austenitic structure. This chromium, balanced chromium, will help it provide some corrosion resistance, right? And this carbon, 0.03% of carbon, right? It has a role to play in a solid solution, but it is maintained 0.03 in a L grade, low carbon grade, because they have to tie up with moly, titanium, niobium, and tantalum. We will discuss this why there is a moly, titanium, niobium, tantalum. Okay. Now the balance between this microstructure is such that there is most of the time 90 to 100% austenite is there, but 5 to 8 percentage ferrite is a solidified microstructure is there. Now, their austenitic stainless steels are characterized by strength, good strength, and toughness, and they provide good temperature oxidation resistance more than 538 degrees Celsius. And the typical grades used by the industry are 302, 304, 310, 316, 324, and 347. These are the most commercial grades used by the industry. Okay, so here you see the microstructure of austenitic stainless steel. You see austenite grains where you have some, some bends are there, and the most of the austenitic grain structure is very typical to identify using the optical microscopy. This is for 316L austenitic stainless steel grade. Okay, now if I have to discuss about the weldability of austenitic stainless steel. So generally it is easiest in the stainless steel family to weld. The this stainless steel family contain many stainless steel, but this one is the easiest to weld. But there are certain issues or susceptibility to or some problems related to weldability. These are hot cracking, then intergranular corrosion due to sensitization, then loss of ductility due to intermetallic phase precipitations and distortion. So we have to take care of these issues. Let us discuss this one by one, these issues, to better understand the welding or weldability of austenitic stainless steel. So here on your screen you have a just a tie like just like your tie shape phase diagram. This phase diagram is is very important for understanding the uh, solidification mode of austenitic stainless steel. So this is pseudo-binary phase diagram. Pseudo means they are artificial binary diagram, but this is generally iron, chromium, and nickel ternary diagram, but is a section of this diagram in a two-dimensional way. And you see that you see a different alphabet like A, AF, FA, ANF, right? So on the bottom side, you see a different, say, terms like austenite plus skeletal ferrite, austenite per lithium ferrite, austenite per acicular ferrite, and ferrite per Wiedemann central ferrite. So your austenitic stainless steel can undergo solidification out of the first three, any of the first three. Your solidified austenitic stainless steel can either solidified in a fully austenitic steel, it can be solidified in a ferritic plus austenitic stainless steel. So which solidification mode is better, right? It so generally you see on the phase diagram, on the top everything is liquid, right? And when you move towards left, there will be more nickel in alloying element. When you move toward right, there will be more chromium. So it's all about adjustment of nickel and chromium in a composition. But when your composition is cooling through liquid and is passed through a two-phase region, liquid plus austenite, and it's solidifying as a fully austenitic structure. That is shown with the reaction is shown over here. It is a fully austenitic structure. Composition is such that you have a balanced nickel and just more chromium, but medium nickel. Your composition is going to cool from this region, and you have a ferrite plus austenite, that is F plus A region. Then you have a some composition which first solidifies as a ferrite. Not first solidification mode is not austenite, but the first solidification mode is F ferrite, that is 100% ferrite, right? So say this ferrite plus austenite, it is passing through this intermediate region, right? That is most of the time for the higher chromium and balanced nickel, that is this region. And some composition cools, not austenitic, but obviously duplex. This will solidify from this region F. So you can understand this diagram, how this diagram is helpful, and how the various solidification modes are developing. So we have to take care that most of the time when we are welding, our weld should solidify in a FA mode, preferably in a ferritic austenitic mode, because this A and AF mode, this A and AF mode are susceptible to hot cracking. Hot cracking means the moment you finish weld, you will see a crack. Now, let us move to a reason how this crack is appearing, right? So, it's hot cracking phenomena is a very common phenomena with welding of Ostratic stainless steel, particularly. And hot cracking is a crack in a weld metal or heat affected zone. Now you understand what is weld metal, what is heat affected zone. But this crack is forming when the temperature cool from the elevated temperature to room temperature. So there are two types of hot cracks. One that is appearing in a weld metal, you will identify as a solidification crack, and one which is there in the heat affected zone, you call it as a liquidation cracks. So both are cracks, but their both place of origin is different, right? One which is appearing in a weld metal is a solidification crack. One which is appearing in heat affected zone is known as liquidation cracks. Now let us move to a solidification cracking. Now, how solidification cracking is occurring, right? So there are two conditions, but first there the microstructure, there be some presence of low melting points material, elements with low melting point phases are there. Low melting points means if there are sulfur and phosphorus in a composition, the sulfur and phosphorus are not going to freeze at the temperature the rest of the alloying element are freezing, right? So there are the freezing at a very low temperature. So what happens? Most of the matrix has been solidified, but these sulfur and phosphorus are not. So what they do, they just develop a crack sensitive microstructure. We'll see what is kind of microstructure is developing, but there should be a condition like weld metal is subjected to some restraint or some mechanically strain condition. If some the thermally or mechanically strain is there, right? So this low melting point, how they are become responsible for the cracking, that we can understand from this diagram. When the weld is cooling, either you have a dendritic solidification or you have cellular solidification. So when your welding is, when your composition is cooling, what will happen? uh, at the solidification front, there will be some rejection of the alloying elements, like sulfur and phosphorus will get rejected, right? Because when you are freezing, this sulfur and phosphorus has no solubility in a ferrite, sorry, no solubility in a austenite. So as a result, what will happen? They will throw out of the dendrites, and they are thrown into the liquid phase. So when they are thrown into liquid phase, they have the tendency to uh, you know they have the tendency to go inside the interdendritic region, like, or sometimes if it is cellular structure, they are more likely to uh, accommodate or go inside the grain boundaries. So what will happen? This, when your weld is undergoing cooling, there will be shrinkage stresses will be developed, and this liquid film, you can see this liquid film will not support the stress. So what will happen? There will be a disbonding, or there will be a gap created between the grains, and you called it as a solidification cracking, right? So these kind of cracks are created, that is because of the presence of these low melting point elements, right? So uh, over in the picture you can see a literally a crack, right? You see a crack. These are the solidified grains, as you have seen in the schematic, and in between the grain, on the grain boundary, you see a very clear kind of crack. that is a weld solidification crack in 310 stainless steel weld deposit, and is a very common phenomena. Now the question is how to get rid of it, how to solve this problem. Okay, so before we move to this, uh, we also have to understand the crack formed in a heat affected zone. So liquidation cracking, right, that form due to grain boundary segregation and enrichment, that leads to development of low melting phases. So most of the time it develops in the heat affected zone of the base metal or on the previously deposited weld beads. So this liquidation cracking, you know, just how we can understand the liquidation cracking. For example, you see a picture C and D, right? You see a C and this both picture. First, you see when you are moving your heat source, when you are depositing weld metal, you know, this is going to be your location, and this is going to be your weld pool, right? Which is in a liquid state. So this area will be in a liquid state, and this area is almost pasty. How it is pasty? Because most of the time you see some grains or some solidification dendrites has already started from the base metal. So in a just the heat affected zone, this is the area where the heat affected zone is there. So the grains under the uh, liquid zone will be most of the time in a compressive stresses. But whenever they are moved, when the heat source is moved, and this area is now pasty because the your heat source is moved. So now you have solidification in progress when you move from left to right. So this weld pool, when it progressing, you have a trail that is in a pasty liquid, that is in a solid plus liquid phases. The heat affected zone will be in a, the grains in a heat affected zone will be in tensile stresses because the shrinkage is developed because of the solidification, right? That is solidification shrinkage. And if there is a presence of liquid films under the tensile stresses, under the action of the tensile stresses, these grains will get apart. You know, there'll be some crack between the grains, and you call this as a liquidation cracking in the heat affected zone. So this schematic is from the Shindo cow book, and is very helpful to understand the phenomena of liquidation cracking in a heat affected zone. That is because of the presence of, you know, this low melting point liquid, sulfur and phosphorus mainly, and presence of residue stresses. So tensile stresses are not favored for this liquidation cracking, right? Okay. Now, how to make sure that our austenitic stainless steel weld metal will not crack? You know, it's about uh, significance of delta ferrite, because he was Hull who reported in sometimes in 1967, if your weld containing around 5 to 10 percentage of delta ferrite in a room temperature microstructure, you have resistance to hot cracking. It means you ensure that your weld metal will not have either a solidification cracking or liquidation cracking. But again, the 5 to 10% of delta ferrite is this thumb rule is again not it is a industrially accepted thumb rule, but it is not as clear because the solidification cracking resistance is also determined by the solidification mode. So you can refer back to that slide, right? The mode of solidification: A mode means fully austenitic mode, primary austenite, secondary ferrite, this is F mode, then F mode, first ferrite, second austenite, this is Fa mode, and then F mode, fully ferritic mode. So when your stainless steel is solidifying in a primary delta ferrite mode, you have a resistance to hot cracking. Just for information, some composition of the, you know, stainless steels, right? Most of the time 1682, 304, 304, 316, 316L, 309, 347. You see, they uh, they have a ferrite number most of the time 2 to 3. So there are resistance to solidification cracking. So solidification cracking here, the 2 number is more susceptible, because there should be most of the time 3 to 8, right? So you see some weld metal 316, 308, 316, 308. Minimum ferrite number required is generally 2 to 6%, right? Then you can ensure resistance to solidification cracking. So we will come to know this, how to measure this ferrite, what are the ways to measure this ferrite, the subsequent friend. But just to explain you the solidification mode, the cracking susceptibility versus this, chromium and nickel composition. You see, when your composition is cooling from the A mode, that is fully Ostratic mode, you have high cracking susceptibility. And where your composition is cooling from first austenite and second ferrite, that is primary austenite and secondary ferrite, you have cracking susceptibility comparatively reduced, but you have certain composition, right? But when your composition is first ferrite and second austenite, you have a better situation. You means crack will not form. There is a crack susceptibility will become very less. So you must ensure that your solidification mode is generally FA. And how to maintain this solidification mode? Okay, this solidification mode will depend on type of composition and your type of filler you use. So again, you refer back this 3 ternary diagram or tie-shaped diagram. Here over you can see this composition, right, where the austenite is first formed and the second phase is just in an interdendritic region, right? In a second composition, this line, your first phase is delta ferrite and secondary phase is austenite. Here over you have austenite. This is more good situation. Primary ferrite solidification is more beneficial. It is a very good condition where you can prevent solidification cracking. Primary delta ferrite, secondary austenite. So always remember, your composition should cool from primary ferrite and secondary austenite. So this is a thumb rule, right? So here over again you can see the black region is ferrite and white region is austenite. So you should avoid A and AF mode when you are welding. You can you have to manage the FA mode with Ostratic stainless steel, and with a duplex stainless steel, obviously it will be solidifying with a 100% ferrite. Okay, now how to ensure this some amount of delta ferrite in your microstructure? Because filler metal compositions are some filler metal composition are such that you have a generally 5 to 10% of delta ferrite in your microstructure. So what is the reason of this small amount of delta ferrite? Because small amount of delta ferrites creates a magic, because it doesn't allow the crack to form. So the technical or the welding metallurgical reason is this delta ferrite will reject less sulfur and phosphorus. Most of the time the sulfur and phosphorus are creating problem. So sulfur and phosphorus are more soluble in your delta ferrite region. It works as a sink, for this low melting point elements like sulfur and phosphorus. So it swallow sulfur and phosphorus in your composition, and again the diffusion, as I have told you, there will be a diffusion of alloying element. So these alloying elements have a less diffusion in austenite. So most of the time, austenite will not allow sulfur and phosphorus diffusion inside it. So it is the ferrite which allows more diffusion of sulfur and phosphorus. So that is why you get rid of the solidification cracking, right? So when you are welding, before if you want to predict your microstructure before welding, you have to take help of some diagrams. These diagrams, helpful diagrams, were developed from the 1940s to 1990s time. The primary diagram was the Scaffold constitution diagram. So how to use this diagram? Uh, you have to calculate the composition of the steel, because in your steel there will be a nickel, carbon, manganese. When you calculate it, you get a nickel equivalent using this formula, and you have to calculate chromium equivalent using the composition of chromium, molybdenum, silicon, and niobium. Then you see where your composition is lying, right? When you get a nickel equivalent and chromium equivalent, you will be somewhere over here, austenite. Then your structure or weld metal is going, or it is going to solidify through fully austratic mode. That is more dangerous. If you fall somewhere over here, there is 5% ferrite, 10% ferrite, then you are in a win-win situation. It means your weld metal is not going to crack. So there is a most favorable condition if your composition is cooling through this region. Now sometimes I will I'm willing to take the specialized class on the use of this constitution diagram using practical application, but this today the time does not permit me. But this is overall a picture of the Scaffold constitution diagram, so you students may be more familiar. Then there will be a diagram called the DeLong constitution diagram, that is developed in 1949. This was developed in 1940s, and this during World War II, DeLong constitution diagram. So here over you get a percentage of ferrite, like 5%, 10%, 20%. Now this diagram was modified, and that give ferrite number, that is 0, 2, 4, 6, 8, and there is also some so this diagram is introduced with a ferrite number instead of percentage ferrite. Now the latest is a WRC, that stands for the Welding Research Council diagram developed by the Welding Research Council, the WRC 1992 version. This version is now latest. This version is developed by Dr. Kotecki and Stewart in US under the fund of Welding Research Council UK, and these diagrams will give you the exact. This diagram will helpful to you to predict the solidification mode. When you are welding with Ostratic stainless steel, when you are using some filler metal, you have to take into account the nickel equivalent, chromium equivalent. You see where your position is. If your position is between 2 to 8, to ensure 2 to 8 prediction, you are on safer side. It means weld solidification crack will not happen. But if your composition is somewhere over here, A region, right, you are likely to end up with solidification crack, right? So this is WRC constitution diagram. It is now latest for your information. Now the second problem with, or second issue with the Ostratic stainless steel is, it is a chromium carbide precipitation or the weld sensitization. So to understand it, you see a thermal cycle. You see some peak like A peak, second number peak, third number of peak. It is the temperature through which your region of the weld is experiencing. If your fusion zone is experiencing one number peak, the next fusion zone is experiencing two number of peak, your third adjacent region is experiencing third number of peak. So when this thermal cycle, when it is heating and cooling in some band of temperature region, like this band, like TA and TB, you have a more complications. How these complications? Because chromium from your composition will combine with the carbon, with the available carbon, and it forms chromium carbide precipitation at the grain boundary. You see here over in your just adjacent to fusion zone, you have a grain boundary like this, but just in your fusion boundary, next to your fusion boundary, in your sensitized region, in your heat affected zone region, you see a chromium carbide is precipitate along the grain boundary. Now this chromium carbide Cr23C6 is having a very a bad effect on the corrosion resistance. This Cr23C6 precipitation, this curve is generally, it's technically from the ranging from the 4 at degrees Celsius to somewhere 800, 480 to generally 480 to 870, right? This CR23 C6 precipitation band is very bad. So what is the reason for this chromium carbide precipitation? Generally, you have to take care of the 600 to 850 degrees Celsius, but technically 480 to 870 is more prone for most of the stainless steel. So what happens, your grain, the grain will contain chromium, right? Because it is a Ostratic stainless steel, is a stainless steel, right? So what will happen, your chromium will diffuse and combine with carbon. But you know why? The only the area, or the only the region nearby the grain boundary is uh, depleted of the chromium, because chromium cannot diffuse faster, right? But the carbon is a smaller atom, it will diffuse very faster. So what will happen, the chromium most of the time be quickly combined from the area nearby the grain boundary, and it will combine with the carbon, and Cr23C6 will be formed along the grain boundary. So here in your actual picture you see a severe chromium carbide precipitation along the grain boundary. Now this chromium carbide precipitation will have a uh, very poor corrosion resistance, right? So it is a picture of the heat affected zone IGC attack, intercorrosion corrosion attack, in SS304 stainless steel, where the carbon is only 0.05 percentage. Most of the time carbon is maintained below 0.03, so that carbon will not be available and the problem will not be there, right? If carbon is available, then only carbon can combine with chromium, right? And it is happening in the most of the time in this temperature range, right? And technically 480 to 870 degrees Celsius is the temperature in which the sensitization will happen. So this is the curve. This is showing the sensitization curve, right? Now, when you can reduce the carbon, when you reduce the more carbon, you have a less danger. Like if you have a 0.03% carbon in a composition, you are away. Your cooling will not be through, when you are cooling through this zone, say 480 to 870, you are away. Means your cooling curve will be away, quite away from this nose, from this C-shaped nose. So you have less danger. If you fall in this region, if you mistakenly fall in through this cooling curve, fall through this region, you have every possibility for corrosion carbide precipitation or sensitization. Okay, now how to avoid desensitization? Once you have a sensitization, right, the remedy is, the troubleshooting is, you have to heat it the wet joint through 1000 to 11 degrees Celsius to dissolve all chromium carbides. This chromium will go back into the solution. Or if you use a stabilized grade of stainless steel like 321 and 347, this will contain titanium and niobium. So what will the titanium niobium will do? You come on this diagram, because titanium and niobium has a more attraction for carbon than chromium has. So before chromium combines with carbon, the titanium and niobium will combine with carbon at a upper temperature. So it takes first chance to combine with carbon, niobium and titanium. So this 321 stainless steel, that is stabilized stainless steel, it is containing titanium, and 347 stainless steel, that is sensitized stainless steel, it is added with niobium in their composition, right? And their filler, their matching filler also contains some titanium and niobium. So their composition, so before chromium carbide precipitation takes place, or before chromium tries to combine with carbon, titanium and niobium will combine with carbon, and this titanium niobium will not have any bad effect on the corrosion resistance, right? So there is a birth of 321 and 347 stainless steel, that is stabilized stainless steel. Now the stabilized stainless steel again have some issues. The issues is called the night line attack. This night line attack, in simply terms, It is because of the welding cycle, or heating cycle. Again, this titanium carbide or the niobium carbide will dissolve. Again, the carbon will go back into the solution and combine with chromium. So there'll be a reprecipitation of chromium carbides. So you have to avoid, and this attack. So what you have to do is you have to go for the stress relief heat treatment. If you go for stress relief heat treatment, again this chromium carbide precipitation will dissolve, go back into the solution, and you have some sufficient time. But provided you have a fast cooling, when from your 1000 to 11 degrees Celsius temperature, you have to go for quick cooling. So you should not provide sufficient time for chromium to combine with carbon, right? So this is the remedy of this knife line attack. Okay, so these are the remedy as I just mentioned you. Or either if you can add some rare earth elements like lanthanum, selenium, which are now the latest development in the welding steel. So you can get rid of the knife line attack. So again, problem is the stress corrosion cracking, because your Ostratic stainless steel may be subjected to stress corrosion cracking. You will see the crack is of very typical type, right? It is of branch like crack, kind of lightning type of crack. It is happening because of the when your steel is exposed to stress condition, and the composition is such that you have a chloride exposure to chloride ion. Like if you use the Ostratic stainless steel in a for saline application, for shipbuilding work, or for the industries where the exposure is of chloride or sulfide, right? Your stress corrosion crack will form. So predicting the weld metal microstructure. Now we are moving to a next generation of stainless steel, that is duplex stainless steel. Duplex stainless steel is a very outstanding material because it is involving both the property of austenite and ferrite, ductility from austenite, and superior stress corrosion resistance from the ferrite. But the role of alloying element is such that it has adjusted composition so that there is 50% ferrite and 50% of austenite, right, in their microstructure. So most typical grade is 2205, that is 22% chromium and 5% nickel. And there is also presence of some molybdenum. Now there is a role of nitrogen. I'll take you to the composition of this. But the most important duplex stainless steels, they are meant for improving the chloride stress corrosion cracking, right? They are meant for improving the fabricability. It means they are welded as good as Ostratic stainless steel, but they are as good as resistance to chloride stress resistance as ferritic stainless steel. So these have a highest pitting and stress corrosion resistance. They are most of the time used in a power plant or oil and gas production fabrication. So here you see a duplex microstructure. You have austratic grain, that is light phase, and you have dark phase as a ferrite grains. Generally, they base metal microstructure is 50-50, but the microstructure of weld metal will vary from 35 to 65, right? So you have a 35 to 65 of ferrite and rest is austenite. Now you see these are the typical composition of various duplex stainless steel. For characterizing the duplex stainless steel, important properties: pitting resistance, equivalent number, that is resistance to pitting and corrosion resistance, pitting and pitting resistance. So you see the most typical grades. There are many grades, developed into many grades from PRN 32 to as good as PRN 40. There is a super duplex stainless steel, but the most typical is used by the industries 2205. This grade is now used widely in industry. Now, what is more special with the duplex stainless steel? There is a presence of nitrogen. So this nitrogen is a strong austenite former. So what does it do? Nitrogen will stabilize the austenite phase, as well as the solidified structure will have a less ferrite and more austenite, right? So these welding of duplex stainless steel is done with a special kind of filler metal where you have a overmatching nickel alloying element. But you have to care about the heat treatment, and you can also use nitrogen as a shielding gas, because you know the nitrogen has an important role to play, and you have to ensure low impurities in base metal, filler metal. So this is a ternary phase diagram which you have seen for the Ostratic stainless steel. In Ostratic stainless steel we are falling in this white region, right, most of the time. But in a duplex stainless steel we are have two phase structure, right? So we are falling in this region, in this gray belt, right, where composition is from the liquid, it is falling inside this curve. So you have a two-phase structure here over ferrite and austenite. So you have a two-phase structure region, and your most of the commercial composition is in this belt. Now, this weldability, it is very typical to weld the duplex stainless steel, but I can ensure. But what we have to ensure that we have to use a nickel enriched filler metal, and we have to control the ferrite, because if your composition or your weld metal is cooling too fast, there will be high ferrite. It will be slowly cooled. You have every possibility for these intermetallic compounds like nitride, carbides formation. If you go with the correct cooling, you have a generally 30 to 60% ferrite. You see this temperature versus composition curve. You see, you have to avoid this cooling range, right? So you have to avoid this nose. So you have to cool, your compression should cool through this, right? It should not have a fast cooling, it should not have a slow cooling, but it should have correct cooling. But you cannot use the duplex stainless steel above 250 max temperature, because if you attempt to make about 250 degrees Celsius temperature during your service application, you have every danger of these phases, intermetallic phases, and these phases are bad for corrosion resistance, right? And again, with WRC 1992 diagram, you can predict, but your duplex stainless steel is going to solidify with in this region, right, where my cursor is moving. Your composition is falling in this, so you have 35 to generally 65 percentage. Okay, so you have no danger for solidification cracking. Remember, your duplex stainless steel will not undergo solidification cracking, but it has danger for nitride and carbide or intermetallic precipitation. So you have to ensure ferrite generally from 30 to 60 percentage of ferrite, right? So ferrite control is very necessary. So how to measure this ferrite? For Ostratic or for the duplex stainless steel, there are instrument method. The instrument method is AWSTM A4.2, that is a ferritoscope instrument. The ferritoscope instruments will measure the weld metal ferrite composition. You have to ensure 35 to 65 using, it is a non-destructive kind of measurement technique, or you have a destructive ferrite measurement using that is ASTM E562, that is a fraction, volume fraction measurement, where you make you prepare the microstructure, you just make identify the ferrite grain and austenite grains. There will be statistics, some statistics will be used, and you have some volumetric ferrite, that is ASTM E562 method. Now, so I think I have to end this class, because end up this webinar, because the time will not permit, and I could only complete the the most weldable steel, that is austenitic and duplex stainless steel. I have reference from the Shindo Cow book. So for the students who are very much interested, I'll recommend you to go through this Shindo Cow book and Welding Metallurgy and Weldability by Lippard and Dr. Koteki. And you can visit my blog. I'm into writing of a technical blog, and I'm now taking many questions from the academia, from the research scholar, or from the industry people, and I handle the technical issues and filler metal selection queries on my welding blog. From my research experience, I will try my best uh, to satisfy you with the technical answer. So here is my blog. You can also subscribe my blog for receiving, many question answer, a technical question answer post on your email. So here you can go weldingknowledge.co.in for your any question, and I'm